We have described impulse, or the change in momentum, both quantitatively, i.e. using equations, using numbers, and qualitatively. What happens when an object stops, what happens when an object is starting. Today we're going to describe impulse graphically. We're going to provide you with a force versus time graph today. And what I want you to remember is whenever you see that force versus time graph, force on the y-axis, time on the x-axis, you should think three words. Three words. Those three words are the following. Area equals impulse. The area between the line and the x-axis on a force versus time graph will always be impulse. Now, you're not always asked to find the impulse. You may be asked to solve for a different variable. It doesn't matter. I don't care what you're asked to solve for. The first thing that should come to your mind is area equals impulse. Just like when we see force and time in the same question, we think impulse mathematically. Just like when we see a funny angle, we think 5 words, I don't like funny angles. Okay, now when we see a force versus time graph, 3 words are going to automatically come to our mind. Area equals impulse. Now, you see in the graph that I have up on the board right now, there is some of the line that is above the x-axis, right here, and we have some of the line that is below the x-axis, right here. The area that is above the x-axis is going to be positive. And the area that is below the x-axis, we're going to make negative. So in this case, you would get a positive impulse as a result of the blue section, and you would get a negative impulse as a result of the green section, because, of course, above the x-axis is a positive force, which causes an increase in momentum. Below the x-axis is a negative force, which causes a decrease in momentum, or an increase in the opposite direction, which is still a negative impulse. Now, you may be asked in a question like this just to solve for the impulse. And if you are, good, that's easy. Right? Area equals impulse. Get the area of the graph. But you may be asked to solve for something else, like, for instance, change in velocity or even mass, maybe. If you're asked to solve for something beyond the impulse, which is just the area, then I still want you to find the area, but then, after you've found the area, use impulse or area equals m times delta v. That's a valid equation, right? Impulse is equal to m times delta v. What I don't want you to use ever in one of these questions, although technically valid, I don't want you to use impulse is equal to F times delta t. Why not? Anybody provide a suggestion for me as to why I don't want you to use F times delta t, even though it's technically valid anytime you have an impulse? Perfect. The force is changing. Now, technically, when we use that equation, delta p is equal to F times t, that force means either a constant value of force, which we clearly don't have here, or an average force. We do have an average force here, right? But what is it? Like, what is the value of the average force there? Okay, it is not worth your time to try to use F times delta t, even though it's technically valid. Reason being, in most situations, the average force is just too difficult to find for the graph. So, you should automatically be thinking area equals impulse, and then, if you need to go further, you should be thinking impulse or area is equal to m times delta v. You should never think impulse is equal to F times delta t in the context of one of these graphs. Now, if you came across a situation like this, here's the force versus time graph, and it's a nice straight line like that, well, then you could use this, right? Because the force is constant. I'm going to still suggest you don't. Okay, I'm going to still suggest you don't use it, just because I want to keep you in the habit of not using F times delta t. even though it would work in that situation. Okay? There's always another way, so let's use the other way that will always work, not the way that will work occasionally, like F times delta T. All right, I'd like to take a look at an example question. This is in the booklet that you got on the very first day of the semester here. Example number 1 for concept 14 says, a 4,500 kilogram truck begins at rest and accelerates over time as illustrated by the graph. Determine the impulse experienced by the truck and the final speed of the truck. Now, it's a little bit difficult to see things on the board right now on this graph. Okay, the numbers are kind of a little faint and the units and so on. I believe on your paper you can see things just a little bit better, right? Notice first of all that this is a force versus time graph. And whenever we see a force versus time graph, we're going to think 3 words, area equals impulse. Not a bad idea to even write that down, just to remind me that that's what I'm going to do for this. Or at least that's where I'm going to start. Maybe that's all I'm going to do. Maybe it's just my starting point. It doesn't really matter. I'm going to do this, area equals impulse. Also note, every time you look at a graph, you should look at the axes. Look at the units on the axes. On the x-axis, note the units are seconds. That's fine, because that's what I'm used to using, right? Those are the standard units. But on the y-axis, you notice it says force times 1,000 newtons. Last semester on the diploma exam, just a couple weeks ago, there was a question. It wasn't this graph. It wasn't force versus time. It was force versus, this is going to sound odd, but it was force as a function of 1 over r squared. 1 over r squared was on the x-axis. Okay, we'll deal with graphs like that later on through the semester. But that doesn't really matter for what I wanted to point, the point that I wanted to make here today. The point that I want to make here today was on the y-axis, it was just like this. It said force, bracket, times 1,000 newtons. When I saw that graph, I thought, okay, we can nail this. This is a question that we can do a really, really good job on. And I chatted with a couple people after the exam. People were asking me about that question. Is this what you do? And I'm like, yeah, it's good. Sounds like you nailed it. Sounds like you did a good job on it. And then I said to a couple people, did you remember to times the y-axis by 1,000? And some people said, yeah. And a couple people said, what? Times it by 1,000? And I said, yeah, the y-axis said times 1,000 newtons, just like this one does, right? And there was maybe a third of the people that I talked to that forgot to do that. They knew exactly what they're doing on the question, but yet they just didn't pay close enough attention to use the right units on the y-axis. Okay, don't get a question wrong because of that. Okay, every time you see a graph, look at the axes, look at the units, and if it's not standard, then circle it and draw attention to it, just like we did here. Okay, we want to find the impulse experienced by the truck and the final speed. We'll just get the impulse first. We have 4 different sections, really. 3 triangles and a rectangle. We're going to say the area of the first triangle is 1/2 base times height. That's going to be 1/2 of the base. What's the base here? Hard to see it on the board, but again, I think you can see it on your handout. The base is 5, yeah. What's the height? 15. 15? No, it's not 15. What is it? 15,000. Don't forget that times 1,000, right? It's not 15 newtons, it's 15,000 newtons. We do the math there, we get 37,500 newtons. Now the second area is base times height, because it's just a rectangle. The base here goes from 5 to 15, and the height is still 15,000. So we're going to say that's 150,000. The third one, it's triangle again. The base goes from 15 to 20, so the base is 5. The height is 15,000, which is 37,500. And finally, the fourth one, we're going to say it's 1/2. Once again, a base, which is 5, times the height, which is goes down to 15 again, 15,000, which is 37,500 Newton seconds. Is that right? We haven't combined anything yet, but are those not right numbers? What's wrong? Jamie, what's wrong? Yeah, the last one should be negative, right? The height of that is below the x-axis, so we're going to make that negative 15,000. That makes this one negative 37,500, right? Area above the x-axis is positive. Area below the x-axis is negative. Let's add these up. When we do, we end up getting 187,500. There's my impulse, 187,500. Area equals impulse. But we're not done because we're asked to find the final speed of the truck. What else am I allowed to do in this question? Well, I can't use F times T. Remember I said don't ever try using F times T in one of these questions. So the only other thing that I have at my disposal is m times delta v. We know the impulse, and we know the mass. Solve for delta v. The impulse is 187,500 divided by the mass of 4,500 kilograms. And that gives me a delta v of 42 meters per second. Now, what am I technically asked to find here? Impulse and final speed. What have I technically just found? Change in speed or change in velocity, right? But if the initial is 0, then isn't the final velocity just the same as the change? Yeah. Now, be careful though. What if they said the initial velocity was 5 meters per second? Then the final velocity would be 47 meters per second. We changed by 42. We increased by 42, right? If my initial was 5, then my final would be 47. Yeah. Right, delta V is VF minus VI. So VF would be delta V plus VI. Right? In this case, it doesn't matter, right? But if the initial velocity wasn't 0, then it would matter. And I guarantee you, if you forgot to add it, if you just found delta V, and this is a multiple choice question, that's one of your options. And you're going to walk out of there thinking you got it right, but you didn't. Because, once again, you were careless. Yep.
Just want to clarify,
yep.
We always use the numbers on the graphs for significant digits?
Yeah, you know what? I wouldn't worry about significant digits for a graphing question. Now, they will round it to a certain number of digits, but it's either going to be multiple choice where it's rounded for you, or it's numeric response where they say round it to 3 digits. So I wouldn't lose any sleep over that. At least if you were in my class in Physics 20, we didn't pay any attention to significant digits with graphs. Okay, and it's not something that we really have to worry about. Technically, actually, it would be, the impulse would be 2 times 10 to the 4, right? As opposed to 1.9. But. All right, I'd like you to take a look at now worksheet number 2, question number 9. You did the first 8 questions already, up to the graphing question. Now let's take a look at the last one, see what you can do with that over the next couple minutes. All right, let's have a look at that question number 9 now. It says, calculate the impulse experienced by a 4-kilogram object represented in the graph below, and what's the object's change in velocity? So similar to what we just did for our example question. 3 words should automatically come to mind right now. They are area equals impulse. Area is equal to impulse. And then we're going to take a look at our axes to make sure that our units are standard units. We have newtons, we have seconds. All right, we're good there. Okay, let's find the area here. The area of this graph, it's a lot more straightforward than the example was in terms of finding the area. Just one simple triangle, 1/2 base times height. The base goes from 0 to 10, so the base is 10. The height goes from 0 to 4, so we're going to say 1/2 of 10 times 4 gives me 20 Newton seconds for the impulse. So half of it's done. Now we want to find the change in velocity. Well, we can't use F times T, even if we could. really wouldn't be very useful to me, right? So I'm going to say rather delta P is equal to m times delta V. And I'm going to rearrange that to solve for delta V. Take the m down by dividing. I get P, delta P over m. 20 Newton seconds over the mass of 4 kilograms gives me a change in velocity of 5.0 meters per second. We got positives there. Should we have gotten positives for impulse and for delta V? Yeah, if the impulse is positive, which it should be because we're above the x-axis, and we're moving in the positive direction, then that means our change in velocity should be positive as well, right? We should be speeding up. No, hold on. No, I'm glad you said that, actually. Okay, Isaiah said we're speeding up and then we slow back down. No, we're not slowing back down. We're not slowing back down at all. We're decreasing the force. We're pushing on it forward right here, which causes it to speed up. We're pushing on it forward even harder, which causes it to speed up. We're pushing on it forward with less force, but that still causes it to speed up because it's a forward force. Does that make sense?
So like from the top of the graph, when the force is 4 compared to when the force is say 2, the velocity is higher?
The velocity is increasing, 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 increasing. The velocity continues to increase, just not as quickly, because there's still a positive force causing a positive acceleration. It's just not accelerating as quickly as it was after it reaches the peak there.
What's the slope represent?
What would the slope represent? I don't know. What the slope would represent there.